Carbon's the second most abundant element in the human body and in life. It's about 18% is what I've read. If you think about the percentage of what your body is made of, 18% of it is carbon. And it is the backbone of so many different molecules that are pivotal for life. It's the backbone of DNA. It is the backbone of the foods that we eat. There's a whole branch of chemistry, organic chemistry, that is devoted to understanding how carbon operates in the universe and how it bonds. And so it's important for us to be able to understand carbon in particular if we really want to understand life. So let's start from the simplest form, the single carbon atom. So as we look at carbon on the periodic table of elements, we see in the upper left-hand corner of the symbol C that it has an atomic number of 6. That tells us that it has 6 protons. And then to the right, we have this value, the atomic mass units. That's a relative value. We can't directly measure a carbon atom, so we say that given that it has 6 protons and 6 neutrons, its atomic mass is 12. Now, it's not exactly 12, and we will explain why that is in a moment. So when we draw the Bohr model of carbon, which is not the most accurate model, but it is a useful model, especially at the high school level, we want to draw a nucleus with 6 protons and 6 neutrons. We would say that the protons are positively charged particles. Remember, we've got these shells or orbitals where the electrons tend to be. Remember, electrons move, so we cannot exactly say where they are in any given moment, but we can say where they are likely to be. So in this first shell or first orbital, we are likely to see as up to 2 electrons in the first shell. Okay. I'm drawing them on the opposite sides because they're both negatively charged particles, which means that they will repel each other, so they would like to be as far away from each other as possible. And we've got a second shell, and in the second shell, we can have up to 8 electrons in this given shell. So shell 1 can have 2 electrons, and shell 2 can have up to 8 electrons. So carbon has 2 choices. Carbon can either figure out a way to give away 4 electrons, or carbon can attempt to acquire 4 electrons. This is really important property of carbon. Carbon can either be an electron donor or an electron receiver because of this unique property that gives carbon incredible flexibility when it comes to how it can bond with other elements. Now, this is the most common form of carbon. Something like 99.99% of carbon is going to be in this form. But there are other forms. We also have carbon-13. Carbon-13 is an isotope, meaning it's a variation. And in this case, we have still 6 protons, but we have 7 neutrons. So I'm going to draw very quickly the same structure, simply adjusting the total number of electrons. Total number of neutrons. The number of electrons have not changed. And then we have carbon-14. Carbon-14, as it suggests, has a total of still 6 protons and 8 neutrons. Now, I'm not drawing it in this model, but because the atomic mass is increasing in these isotopes, these versions, these variations, are significantly heavier than the most common form of carbon. So carbon-12 having an atomic mass of 12, the atomic mass of carbon-13 is approximately 13 something. And then the atomic mass of carbon-14 is going to be, again, these are relative units, so it's a 14 in terms of its total atomic mass. These are incredibly rare. This is something like 1 in a trillion. So for every carbon atom that exists, you have 10 hundredths, thousandths, 10 thousandths, 100 thousandths, 8, 9, yeah. So you have an incredibly small number. That's really poorly written, but let's adjust that. So I think 9 zeros. That's how many carbon atoms exist in this form. Now, in this form, it is very unstable. That those extra neutrons will decay over time, and this will revert closer to either being carbon-13 and eventually carbon-12. So these are the variations of carbon. So carbon can form covalent bonds, sharing electrons with a variety of other atoms to make an infinite variety of structures, which is why it is the backbone of life. At the simplest level, carbon can bond with 2 oxygen atoms to form carbon dioxide. It can bond with 4 hydrogens to form methane gas. Methane is still somewhat unstable. It can easily light on fire, but it is more stable than hydrogen on its own. Carbon can also form covalent bonds with other carbon atoms to form long chains, as we see with triglycerides, which is long chains of fat, of carbon atoms, 16, 18, 20, 22 long. These chains store a tremendous amount of energy that we can release as we break down fat. Carbon can also form sugars, sugar rings. By the most common form would be C6H12O6. It will form this ring structure. And then those rings can bond with other rings, forming hydrogen bonds that will allow these carbon rings to continue to branch. And all of that increases the overall stability of the carbon atoms and the molecule itself. So carbon, I like to think of carbon as like a Lego bricks, where Legos can form a tremendous variety of structures if you have enough bricks. So because a Lego has, let's say 6 pegs, it can form all kinds of unique structures by just snapping the Legos together. Carbon operates in a similar way, and so while life is predominantly made of a couple of elements, it is in the infinite combinations and permutations of how that carbon can bond with other elements that makes all life on Earth be carbon-based.